Hello, and welcome to the device overview for TI's IWR14 and IWR16 series of single-chip CMOS-based mmWave radar sensors. In this video, we'll start with a brief introduction of TI's mmWave sensors, look at the signal processing chain as it relates to these devices, and a few system topologies in which these devices can be deployed. We then get into the details of these devices, touching upon the major functional blocks. Finally, we'll go over the boot modes and a quick overview of the software development platform available for developing with TI's mmWave sensors. Let's start with a brief overview of the devices. The IWR 1443 and 1642 belong to TI's IWR 1X family of single-chip industrial mmWave radar sensors based on FMCW radar technology. These devices are capable of operating in the 76 to 81 GHz band with up to 4 GHz continuous chirp bandwidth. These devices are built with TI's low-power 45 nanometer RF CMOS technology and enable unprecedented levels of integration in an extremely small form factor. These mmWave radar sensors provide an ideal solution for low-power, self-monitored, ultra-accurate radar systems in industrial applications such as building automation, factory automation, drones, material handling, traffic monitoring, and surveillance. Both these devices provide for single-chip radar solutions by integrating analog and digital components, including multiple transmit and receive chains, PLLs, A to D converters, ARM Cortex-R4F MCUs, a C67X DSP or an FFT accelerator, memories, and various input-output interfaces. These devices also feature continuous self-monitoring and calibration of the RF and analog functionality through a separate ARM R4F-based radio processor subsystem, which is responsible for front-end configuration, control, and calibration. This section shows the key features of these devices. These sensors are based on FMCW radar technology with capability to operate in the 76 to 81 GHz frequency range and support chirp bandwidths of up to 4 GHz. Up to 3 transmit and 4 receive chains are provided for MIMO radar operation. TI's mmWave sensors support highly programmable and flexible chirp profiles to support multiple sensing profiles in the same radar frame. The 1443 has an onboard hardware accelerator for FFT operations and continuous false alarm rate or CFAR based detection algorithms, while the 1642 provides a full-featured C67X high-performance DSP core for FMCW signal processing and advanced algorithms such as clustering, tracking, and object classification. There are two ARM Cortex-R4F MCUs running at 200 MHz. One of these is locked and used by the calibration and monitoring engine, that is, the radio subsystem. This R4F is programmed through firmware provided by TI and is not available for user code. However, the second Cortex R4F is available for high-level application processing. The devices support various industry-standard input-output interfaces such as SCAN, SPI, I2C, UART, and support high-speed raw ADC data output using CSI2 and LVDS. This slide shows the components of a typical FMCW radar chain and maps them to the signal processing capabilities of the 14 and 16XX devices. The receiver chain starts with the RF front-end receiving the reflected radar signal, which is mixed with the transmitted signal to generate a beat frequency signal which is delivered to the ADC. The ADC converts the analog signal to digital samples which are pre-processed for digital processing. Successive FFTs are computed on the digitized samples for range, velocity, and angle of arrival calculation. The radar hardware accelerator onboard the 14XX device can be used to offload the FFTs and detection processing to get a point cloud output. The 16XX device can be used to run advanced clustering, tracking, and object classification algorithms using the onboard C674X DSP. Here we show some example applications and corresponding system topologies for the mmWave sensors. First is tank level sensing. Typical industrial fluid level sensors operate on a 2-wire 4 to 20 mA current loop where the sensor wakes up a few times a second to take level measurements and goes back to sleep to achieve the necessary power efficiency. The 14XX device can be paired with an MCU for such an application, with the MCU being the master. The MCU wakes up periodically and powers up the radar sensor. Once the measurement is completed, the MCU shuts down the radar device and goes back to sleep. The second application shows a 14 or 16XX device connected to an external application processor or FPGA over SPI for a drone or industrial robot application. Here, the radar sensor sends point cloud information to the external processor for further processing and decision making. For example, the flight controller of a drone can use the point cloud information provided by the radar sensor to avoid obstacles or make intelligent landing decisions. Another possible application could involve multiple IWR14 or 16 devices connected to a centralized application processor or an FPGA. Such a topology could be used for surround sensing in drones or autonomous forklifts and other similar applications. The last example shows a single 14 or 16XX device which is paired up with an imaging processor such as TI's DM812X for radar and camera fusion. Such a deployment can be used for intelligent traffic monitoring, where the radar can be used for long-range sensing, or to turn the camera on when the object is detected, thus saving camera power, disk storage, and data transmission bandwidth. Moving on to the next section, we'll look at the mmWave sensor devices in more detail to understand the various functional blocks. This picture shows a superimposed block diagram of the IWR1X mmWave radar family. The components outlined green are present only on the 14XX device, while the components in blue are present only on the 16XX device. For example, the 1443 device has 3 transmit chains, whereas the 1642 device has only 2 of them. Therefore, the third TX chain is highlighted in green, which indicates that it is available only on the 1443. The 14XX device consists of 3 main subsystems, which are the RF or analog subsystem, the radar subsystem, and the master subsystem. In addition to these 3 subsystems, the 16XX device also includes the DSP subsystem, which is outlined blue in this picture. Let us look at the RF and analog subsystem in more detail. This subsystem includes the RF and analog circuitry, that is, the synthesizer, the PA, LNA, mixer, IF, and ADC. This subsystem also includes the crystal oscillator and temperature sensors. The RF and analog subsystem can be divided into 3 subcomponents, namely the clock subsystem, the transmit subsystem, and the receive subsystem. We'll take a look at these subcomponents in more detail, starting with the clock subsystem. The clock subsystem generates 76 to 81 GHz frequency from an input reference of 40 MHz crystal. It has an inbuilt oscillator circuit followed by a cleanup PLL and an RF synthesizer circuit. The output of the RF synthesizer is then processed by a 4x multiplier to create the required frequency in the 76 to 81 GHz spectrum. The RF synthesizer output is modulated by the timing engine block in order to create the required waveforms for effective sensor operation. The timing engine is highly flexible and is programmed via the R4F based radio controller subsystem. The output of the RF synthesizer is available at the device pin boundary for multi-chip cascaded configuration. The cleanup PLL also provides a reference clock for the host processor after system wake-up. The clock subsystem also has built-in mechanisms for detecting the presence of a crystal and monitoring the quality of the generated clock. Moving on to the next component of the RF and analog subsystem, which is the transmit subsystem. Depending upon the device, the transmit subsystem consists of 2 or 3 parallel transmit chains. IWR1443 has 3 TX chains, while the 1642 has 2 TX chains. Each transmit chain has independent phase and amplitude control. A maximum of 2 transmit chains can be operational at the same time. However, all 3 chains can be operated together in a time multiplexed fashion. The device also supports binary phase modulation for MIMO radar and interference mitigation. Finally, we look at the receive subsystem. The receive subsystem consists of 4 parallel channels, where each receive channel consists of an LNA, a mixer, IF filtering, A to D conversion, and decimation. All 4 receive channels can be operational at the same time. Individual power down option is also available for system optimization. Unlike conventional real-only receivers, TI's radar sensors support a complex baseband architecture, which uses quadrature mixer and dual IF and ADC chains to provide complex INQ output for each receiver channel. The bandpass IF chain has configurable lower cutoff frequencies above 350 kHz, and the continuous time sigma delta ADC supports bandwidths of up to 15 MHz. We now look at the next functional block, which is the radar subsystem. The radar subsystem is also known as the BSS, or built-in self-test subsystem. It includes the digital front-end, the ramp generator, and an internal processor for control and configuration of the low-level RF, analog, and ramp generator registers. The radar processor is actually a second dedicated ARM Cortex R4F microcontroller running at 200 MHz. Note that this processor is programmed by TI and takes care of RF calibration, self-test, and monitoring functions. This processor is not available for customer application. User applications running on the master subsystem do not have direct access to the radar system. The master system accesses the radar subsystem through well-defined API messages which are sent over hardware mailboxes. This interface is also known as the mmWave link, and TI's mmWave SDK includes the mmWave link API. The next functional block is the master subsystem. The master subsystem includes an ARM Cortex R4F processor clocked at 200 MHz for running user application code. User applications executing on this processor control the overall operation of the device, including radar control via well-defined API messages, radar signal processing, which is assisted by the radar hardware accelerator or DSP, and peripherals for external interface. This subsystem also includes the various external interfaces available on the 14 or 16xx devices. A Quad Serial Peripheral Interface, or QSPI, is available, which can be used to download customer code directly from a serial flash. A CAN interface is included that can be used to communicate directly from the device to a CAN bus. Depending upon the device, CSI2 and LVDS interfaces are included to facilitate high-speed raw ADC data transfer to an external processor or an FPGA. The 14xx device includes both CSI2 and LVDS, while the 16xx includes only LVDS. Note, however, that CSI2 and LVDS on the 14xx are multiplexed, so only one of them can be used at any instant. An SPI/I2C interface is available for Power Management IC or PMIC control. For more complex applications, the device can operate under the control of an external MCU, which can communicate with the 14 or 16xx device over SPI interface. The next functional block is the DSP subsystem. The DSP subsystem, which is available only on 16xx devices, contains TI's high-performance C674X DSP for FMCW signal processing, including FFT and detection, and also advanced radar signal processing. This allows the 16xx to serve as a complete single-chip radar with advanced capabilities for clustering, tracking, and object classification. Next, we look at the radar hardware accelerator, which is the last functional block in this device overview. The radar hardware accelerator is available only on 14xx devices, and it enables offloading certain frequently used computations in FMCW radar signal processing from the main processor. FMCW radar signal processing involves the use of FFT and log magnitude computations in order to obtain a radar image across range, velocity, and angle dimensions. Some of the frequently used functions in FMCW radar signal processing can be done within the radar hardware accelerator, while still retaining the flexibility of implementing other proprietary algorithms in the master system processor. As shown in this diagram, the accelerator contains 2 functional paths. The first functional path is used for FFT and related preprocessing and log magnitude operations. The second functional path provides for CFAR or constant false alarm rate based detection algorithms. Data movement to and from the radar hardware accelerator is based on TI's EDMA or Enhanced Direct Memory Access Controller. Please refer to the Radar Hardware Accelerator User Guide or Radar Hardware Accelerator online training for more details. Having covered the various functional blocks, we now take a brief look at the boot modes available on TI's radar devices. TI's mmWave radar devices support two boot modes, namely flashing mode and functional mode. The desired boot mode is selected by configuring the Sense on Power or SOP pins as described in the device datasheet. Let's talk about the flashing mode first. This boot mode is used to burn or store the program binary image into the QSPI serial flash. When this boot mode is enabled, the bootloader enables the UART driver and expects a data stream consisting of the application binary image. On receiving a valid application binary image, the bootloader stores the binary into appropriate sections of the serial flash. This boot mode could be used during software development to update the application binary on the flash. The second mode, which is the functional or deployment mode, is used to boot the device from the QSPI flash using a previously stored application binary. With this boot mode selected, the bootloader looks for a valid application image in the QSPI flash. On finding a valid image, the bootloader copies the image to the master subsystem's memory to start the boot process. In this way, the device boots up autonomously from the serial flash. In the last part of this presentation, we take a quick look at the software platform available for programming TI's mmWave radar devices. TI's mmWave radar sensors are complemented by a rich software offering which consists of an SDK, TI designs, examples, and tools. The software platform is divided into three main components as shown. The first one is the mmWave SDK, which provides various foundational software components such as TI's SysBIOS, RTOS, and drivers corresponding to the hardware peripherals available on the radar devices. It also includes the mmWave link and mmWave API to enable programming the radar sensor using high-level API. It also includes signal processing libraries for both the C67X DSP and the radar hardware accelerator. Besides the mmWave SDK, the software offering also includes an out-of-box demo, various TI designs, and labs. The out-of-box demo enables the user to quickly evaluate the radar EVM and visualize the range, velocity, and angle of the target object. The TI designs demonstrate the applicability of TI's mmWave radar in specific applications such as level sensing and traffic monitoring. Last but not the least, we have the mmWave Studio, which provides a system estimator tool and raw ADC data capture capabilities. We'll look at the system estimator tool in the next slide. Defining chirp configurations is fundamental to the operation of FMCW radars, and the goal behind the system estimator tool is to simplify the complex task of defining chirp parameters for TI's mmWave radar sensors for the desired sensing configuration. This tool allows the user to provide application-level inputs such as the desired maximum range, velocity, range resolution, velocity resolution, etc., and outputs the chirp configuration, which can be used with the mmWave API to program the sensor accordingly. It also estimates the radar data cube memory requirements corresponding to the chirp configuration and flags out-of-bound parameters as well. This picture shows an architectural diagram of TI's mmWave SDK. The components in blue are provided by the SDK, while the components in red indicate application code. As we can see, the SDK has a modular design and is divided into various layers. Each layer provides a well-defined API to the layer above it, thus abstracting complexity. For instance, the mmWave front-end firmware, which runs on the radar subsystem, completely encapsulates the configuration, control, calibration, and monitoring of the RF and analog functionality. It exports the mmWave link API, using which the master subsystem communicates with it to control and monitor the sensor front-end. The mmWave SDK not only implements the application side of the mmWave link, But it also provides another level of abstraction through the mmWave API. The mmWave API provides high-level functions to program and control the radar frontend. The mmWave API internally uses the mmWave Link API. This picture shows the directory organization of the mmWave SDK. This concludes the overview of TI's industrial millimeter wave radar sensors. To learn more about these devices, please refer to these resources. Thank you.